Wherever you might be, welcome to this, which is our 113th Reading Online Sports Economics Seminar. And I don't know the number of S-Training seminars that they've been online over the last few years, but we are having a joint event today. So we're delighted to welcome everyone who would normally attend the S-Training events, which take place every month. This is also, as I said, it's also a Reading Online Sports Economics Seminar. We meet every week still, and we will continue to do so at least until Christmas, and hopefully afterwards, depending on the demand and supply of talks. I also want to flag up, especially given we've got a wider audience today, the fact that at the end of this current academic period, so just before Christmas, we're going to have a physical in-person conference in Reading. It's called the second Reading Football Economics Workshop. We had our first one just before the pandemic, 13th and 14th of December, meeting in Reading. If you are interested, there is a website and a abstract submission play point. The deadline that's been extended for abstract is the 16th of December, so that's November. That's next week. I will put the links in the chat if you can see it, and if you can't see it, then try emailing me, or if you're on the S-Training network, email either of Andreas or Christoph, who administer the group, and we can get the link to you. That's an in-person conference at the end of the term, just before taking place at the same time as the World Cup semi-finals, and that's a reminder there with the background noise that if your microphone is not on mute, please do leave your microphone on mute as we get going. Without any further delay, we have Jean-Louis Foulley from the University of Montpellier in France, who's going to talk to us in a very timely fashion about the FIFA World Cup, how to adjust probability forecasts of football match outcomes in one-legged knockout tournaments with an application to the FIFA World Cup. If you do have any questions for clarification for Jean-Louis as we go along, please put your hand up and I will interrupt Jean-Louis, and otherwise there'll be plenty of time after Jean-Louis finishes for any kinds of questions and discussion. Jean-Louis, all yours.
Okay, do you see the screen now?
Yep.
Okay. So thanks, James, for giving me the opportunity to have this talk on your Roses seminar, which I have now attended for more than 2.5 years, and which was very beneficial for my personal training in sport economics. Thanks also to Christoph and Andreas for making this joint meeting of Roses and S-Training possible. So I'll talk today about this title, and although it's tasted a little bit technical, I consider it more as an introductory talk than a definitive one, as I know that already many people are working on this subject, especially due to the forthcoming edition of the World Cup. A quick look at the contents of this presentation. A reminder about the knockout tournaments, its main features, and on our objectives. The first part will be a kind of theoretical part, giving probability of outcomes after the different phases of the outcomes, different phases of knockouts, regular time, extra time, and for any time, both in terms of win, draw, loss, and score lines. And the second part will be a longer one about the illustration to the World Cup, first by presenting the data sample and some basic statistics, the marginal and joint distribution, number of goals, fitting them with Poisson distribution, estimating parameter with a generalized linear model. A few words about this problem of penalty shootouts, and finally the different options we have at hand to meet our objectives. Last discussion and a list of reference. So first, the knockout tournaments. It's difficult to talk about knockout tournaments without saying a few words about the stage preceding it, the so-called group stage, which is made of X groups of usually 4 teams playing each other once in one leg or twice in 2 legs against each other. In Euro, we have now 6 groups for 4 teams each. That makes 6 matches per group and a total of 36 matches. In the World Cup, we had now 8 groups, and we had before, as we will see, 6 groups. So that makes a total of 36 or 48 matches. And for instance, in the Champions League, we have 8 groups, as in the World Cup, but it's 2-leg competition, so we'll have 12 matches per group and a total of 96 matches. The knockout stage, what is the main characteristic, is a single elimination tournament. Only winners progress and get the prize. How they are selected, the winner and runner-ups from the group stage, and sometimes some complement among the third for the group stage are qualified for knockout stage per se. So that means a total of 16 teams, and matches are decided among groups, as we saw for the World Cup, A versus B, C versus D, E versus F, and G versus H, or by random draws between seeded and unseeded, as for instance in the Champions League. And this is repeated at each step. So we come up with R16, quarterfinal, semi-final, final, and eventually 3rd place, as in the World Cup or the Euro. So that makes a total Euro and World Cup of 16 matches, and for 2 legs, 29 matches. Now, coming to the format, time format, which is really important and main subject of this talk. We have 3 different phases. We have the full time, what I call regular time, 2 hours of 45 minutes each with a break of 15. And it dates back, I go to the history, and it dates back to the Sheffield Rule in 1877. So it has been a long history. We must include in this regular time the stoppage or additional time added by the referee at the end of each half to compensate for time lost. That could be injury, player substitution, waste time. I don't know if the video assistant is also included in that, probably. So it's usually between 1 and 6 minutes. Afterwards, if there is a tie, we have the extra time, and it dates back 10 years later, 1897 amendments with 2 halves of 15 minutes, a change of position. So it's important, the change of position, because to balance, for instance, for sun, wind, and so forth, and a 5 minutes break on the field. I won't say too much about the episode of golden and silver goal. Golden and at the first winning goal, and silver at the end of the first half in favor of the leading team. They were very controversial, and they are being abandoned now. And if again there is a tie, we have what I call the terminal stage. For a long time, the match has been replayed the day after, if I read properly in the history, and was finally decided by a single coin toss. It was the case, for instance, in the match Italy versus Soviet Union in Italy in the semi-final of Euro 1968, and Italy was qualified that way, beating by a single coin toss. We have to avoid this replay of the match. They came to the penalty shootouts, And the first appearance was in the Euro 1976, a famous one played in Yugoslavia between Czechoslovakia and Germany. It was a strange match because Germany leveled the score 1 minute before the end of regular time, so they went 2-2. The extra time was 0-0, and finally they came to the penalty shootouts, and it was the famous Panenka, Anton Panenka, who scored the winning penalty, and it's all the memory, this kind of kick by Panenka. It happened 20 times now in the history of Europe. For the World Cup, the first appearance, as far as I know, is the semi-final Germany versus France in Sevilla, Spain in 1982. And again, it was 1-1 plus 2-2 in extra time. And finally, Rubesch scored the winning penalty, kicked the winning penalty. It happens 30 times. Now, our objective is the fact that usually all bets and forecasts on a regular time basis, 90 minutes plus stoppage. And what we, in knockout tournaments, we need to know who is going to win and progress to the next step and win the cup. So my purpose was a simple one at start, is propose probability of outcomes in terms of score lines or win, draw, loss for KO tournaments, whatever the time played prior to the penalty shootouts, and probability of eventually winning the KO stages, so as to know who is progressing to the next step. And we'll illustrate that to the FIFA World Cup. So now, what is the basic of a very simple reasoning? Let's notice PQR, the probability of indexed by J, the probability of win, draw, loss after regular time, during extra time per se, and final result, whatever the time played. So we have to look at now, we start with the draw, for instance. So what is the final probability, R2, for a draw? It's P2, Q2. How do you divide that? What does it mean? It means a draw at the end of regular time and a draw during extra time. So the probability is the probability of the first, P2, times the probability of the second given the first, which is by definition Q2. Now for the win, R1, you have two events, A and B. A, what does it mean? You win already at the end of the regular time, or you go to the extra time, so you have a draw in regular time and you win in extra time. So these two, A and B, are mutually exclusive, and their probability, the probability of the union, is the sum of the two probability. The first probability is the probability of win, P1, in regular time, and the second is this probability of P2 times the probability of win in extra time, Q1. So it's very simple formulae to get in terms of win, draw, and loss. Now we can extend it to the score lines the same way, and notice by PQR the same probability after regular time, during extra time, and for any time. For instance, R00 is P00 for regular time times Q00, knowing that it was 0 in regular time. R11, P00, Q11 given 0, plus P11, Q00 given 1. And R10, P10, plus P00, Q10, knowing 0. So it's very simple. These are, I will not elaborate, the general formulae for computing these R probabilities for any given any numbers of goals. Just in passing that there is practically no need for conditioning Q by the score at the end of a regular time. Why that? We will see that from the data, and also we can rely on the independence property of number of goals in disjoint time interval if the process follows a Poisson distribution, Poisson process. Now, if there is still a tie at the end of extra time, we have to recourse to the penalty shootouts with probability S1 for an A win. So now you have to split the probability of a double tie in regular and extra time into two parts, P2, Q2, S1 for probability of team A winning, and P2, Q2, 1 minus 1 for team B, and add them to their winning probability after extra time. So you come up with this quantity, P1 plus P2, Q1 plus P2, Q2, S1. You may assume S1 equal 1/2, just by pure chance, or you may at least assume an indifference principle, that is a uniform distribution on this probability to estimate it from data. We see at the end how to do that. Here, this is an example of this computation. It dates back from the semi-final England versus Denmark in the last Euro 22, played in July 2021 in Wembley. And this is, at the time I was attending the game organized by James for the forecast of this Euro. And we have the following figures for regular time, probability of win, draw, loss, for extra time per se, and any time, and even the final win. So what you can see is an important reduction of the probability of draw, which is half from 28 to about 15, and correspondingly an increase in win and loss. And finally, we estimate the probability of win if including the possibility of penalty shootouts at 55% for England and 45% for Denmark. This is the same regarding the score line for the regular time as for any time. I won't enter in details about all these figures. Just you may notice that with respect to the probability of draw 0-0, 1-1, and 2-2 in regular time, you come up here with quite less, about half probability, 0-0, 0.5 instead of 10, 6.7 instead of 13, and so forth, and an increase in probability of 2-1 and 1-2 as compared to these figures. And finally, the most likely score was 1-0 for any time as compared to 1-1 using regular time. Now, if we move to the FIFA World Cup, first I will describe the sample I used. There is 3 imperatives to meet to select this sample: enough size, homogeneity of the competition, and representativeness of the different editions. For that purpose, I selected the last 9 editions, set 1 and set 2. set one dating from now to 20 years ago, 1998. That means 6th edition, and for set two, the 3 edition before. I would have liked to include the 82 edition, so that will make 40 years, but the knockout was quite different because it started only at the semi-final level. So I think it was not homogeneous with all these editions. That's why I stopped here. So 9 editions. The group stage, we have 8 groups with 4 teams in the set one, and we have 6 groups only with 14 is set two. So that means 32 teams and 24 teams. In the first edition, in the first set, we have 48 matches per edition, and in the second set, 36 matches per edition. So that makes, if you multiply that by the appropriate number, that makes 258 for set one and 108 for set two, and a total of 396 matches. Now, the group stage, we have for every edition 16 teams qualified for R16 quarter, semi-final, third place and final. So for 9 editions, that made 144 matches and a total of 540 matches. Now for the extra time, you will see that the number of matches will be reduced a lot. 49 matches out of these 144 ended at the end of regular time by a tie. That means 44%. And among whose tied match at the end of regular time, only 29, it's not only, 29 ended again with a tie at the end of extra time. So that means about 60% ended again with a tie. So it's you have to keep that in memory, and people should be ready to face the penalty shootouts on account of this high percentage. So a total of 29 matches out of 144, that means 20% as draw at the end. And it's in agreement with what we saw in the example, reduction of the probability of draw. Now, basic statistics, now the number of goals scored by team and match for regular time and extra time, group stage, knockout, group stage with knockout, and knockout. So these numbers are twice the number of matches, because there are 2 goals per match, and the mean, the standard error, and the variance. And you know that for count data, it's important to look to the variance mean ratio, because we have more or less in mind the Poisson distribution, and you know that in a Poisson, variance is equal to the mean. So we are expecting a good ratio of variance to mean not so far from 1. So it's why I give the value of dispersion, the deviation from 1 in percentage of the mean. And this is this figure, which is a parameter entering, for instance, in the negative binomial distribution. You see that there is not much dispersion, especially for the extra time and for the mixed of group stage and knockout. And by the way, you can look at the mean between the number of goals in extra time divided by the non-goal in regular time, and you come up with a ratio of 0.30. That figure we will see later. Now the distribution of number of goals in percentage, 0, 1, 2, 3, 4, 5, 6, 7, 8. And this is for the group stage in blue, red knockout, and here extra time. So you see that the percentage are not so different between group stage and knockout, about 31–32% for 0, 35% for 1, I would say 20% for 2, 8% for 3, and less above. On the contrary, in extra time, we are just 3 classes, 0, 1, and 2, with a high percentage, more than 70% in 0, about 22% in 1, and 6% in 2. Now, just a focus on technical aspects. In fact, you see that we will, as we have learned in classical statistics, usually we will contrast the observed observation to the expectation of this observation under a given model. So we will contrast observed to expected counts in a given cell under a model, what I call here H0. And so what we do in classical statistics, we compute statistics and we look at the p-value of the distribution of the statistics under the null model. So the usual one in that case for discrete data is the Pearson chi-square. And what the likelihood school will prefer the G2, that is the deviance or log likelihood ratio, which is twice the sum observed times the log of observed divided by expectation. All these statistics have an asymptotic chi-square distribution under the null, but there are different patterns of convergence. So what does it mean? It means that we'll get different results for some small sample sizes, and probably we could be very far from the chi-square distribution. So the idea, instead of selecting the test which gives you the result you want, I tried just to use a kind of omnibus test, making a synthesis between these two tests, and this could be done using the power divergence function, which is a continuous function encompassing these two tests and even others. It has been proposed by Noel Cressy, the geostatistician, and Timothy Reade in the 80s, and its formula is the following. It looks a little bit like the G2, sum over observed times observed divided by expecting to the power lambda minus 1 times this factor, 2 divided by lambda 1. Lambda 1 is a real, we'll take here the positive value, and we can realize that for lambda tending to 0, we get the G2, lambda equal to 1, we get the chi-square, and 2/3 as recommended, we are in between the two. So that was the criterion I will use in many instances. And this is illustrated here for the fit of this number of goals for group stage and KO regular time, and trying to look at the fit by the Poisson and the negative binomial. You know that the negative binomial is an extension of the Poisson with an additional parameter called dispersion. And what if you look at here, I reported the Pearson standard residuals. The highest value It's a measure of individual fit cell by cell. And if you are above 2, that means that you don't fit very well the cell. And you see that the test is reject the Poisson, accept the negative binomial. And if you look to the residual, you see that up to 5 goals, the two were very similar, but it was a discrepancy above 5 goals, which makes the difference. And so what we made a box plot of the data for the group stage and knockout. And what happened is we see these three classes, 6, 7, 8, which are the so-called outliers. This means that they are outside the so-called maximum value. The maximum value is above 1.5, the interquartile interval above Q3. So these are outliers, and so we might be inclined to, at least at some stages, to drop them. What is interesting is to look to these extreme score lines, and I have 9 extreme score lines, so that means an average of 1 per edition. And there is this famous 8-0 Germany against Saudi Arabia in 2002, played in Japan, and the memorable 7-1 Germany against Brazil in the semi-final in 2014. And I remember last week, I think, the speaker was talking about the stadium where this match was played in the semi-final, 7-1. And you may think that this extreme score is representing a contrast between the value of the two teams. For instance, if you look at the Elo rating, in some cases there is a big difference. But in the case, for instance, of Germany versus Brazil, it was not the case, because Brazil had a higher score than Germany. So it was really a surprise, this score in the semi-final. For instance, the last edition, England beat Panama by 6-1. It was not so much surprising on account of the difference between the Elo of England and the Elo of Panama. So what I did is at least to test the assumption of fit by the Poisson negative binomial, I dropped these 9 matches, and we got this histogram. And you see in that case that the Poisson and the negative binomial fit quite well the observed data, and they are not different from each other. And this can be expressed in this table, Poisson negative binomial, observed value, expected value, and we see, so you see I dropped the 9 values here. The test has lowered, the statistic of test is quite lower than before, with p-value, high p-value, no difference between the two. So I'm inclined to think that the Poisson is a good fit, despite these 9, I would say, the 9 outliers. For the fit of the number of goals in extra time, using a Poisson distribution, a bit truncated, gives also a very good fit. Now, so we have looked at the marginal distribution number of goals. Now we have to look to the distribution of score lines, so the joint distribution of number of goals. And what we have to do here, just a technical point, in some instances, the order of team doesn't matter. In that case, if we look at the overall level of this score line distribution, doesn't matter to distinguish 1-0 or 0-1. So the score KL is not distinguishable from LK. And we have to pull them into their sum, NKL, big NKL, equal the sum of these two. And for K different for L, and we keep NKK as it is. This is very well known in population genetics, and this triangular structure with just one off-diagonal term has been called TRIMAT by Jacquard in 1970. Now, how you compute the probability that a team score K goals, you compute it as twice this number of draws times the numbers of NKL with the sum over L different from K, and you divide by 2n because there is 2 goals for n match, n being the number of match. So let's see in the example for 3 classes as we observe it in extra time. You report 2n00, n01, n02. If you sum over for this row over the columns, you get this sum. You take this value, divide by 2n, and you have a probability of scoring 0 goals, and so forth. So if you want to compute the distribution of the joint distribution of goals assuming independence, you will take n times pkpl for nkl, and you will multiply by 2 if k is different from L, and by 1 if k equal L. This is very well known in population genetics, and I realized a posteriori was maybe I get involved in football statistics due to my past in genetics. It's maybe a connection I did not anticipate it at start. Now, if we do that for the multinomial and Poisson marginal distribution under independence as compared to the observed score line, and you can see I stop at 5 goals. So this is all the classes 0, 0, 0, 1, 0, 2, 0, 5, 1, 1, and so forth. The observed value, the expected under the multinomial, the expected under the Poisson, the Pearson standard residual, we come up with these statistics, and the p-value, I value of the p-value, which indicates that both models fit the joint distribution quite well. Now we can do the same for extra time. So we have now quite few classes because we see we have only 3 classes of goals. So that makes all these classes, the sample and the expectation. And there is a problem here for 0,2 because we are overestimated these classes as compared to the observed one. And for 1,2, we are underestimated the classes. So the test is still non-significant, but we have this discrepancy at this level. Now, I'm testing the relationship between the result at the regular time and the result at the extra time during the extra time period. So this is the observed value under independence. This is the expected value. Here I have 0, 0, and all the draws pulled together because there are very few data. And you see that we cannot reject the independence between these two stages. Now the model. To estimate the parameter, if we want to go in more detail about the factors influencing this marginal distribution. So in the match M between I and J, we have two goals, Yij1, Yij2, and for simplicity, I will write them I/J and Yj/I. Because this is the goal scored by I facing J, and this is the goal scored by J facing I. So we'll assume a marginal distribution for each of these goals with lambda I/J parameters, and we will put a log linear link function with eta. Hij is a home effect. I will go in more details. Alpha delta Rij, I use the LO rating. This is the difference of rating between team I and J, and this is the mean R bar Ij with coefficient beta. Hij is the home effect affecting I when playing against J. LO ratings, the difference in strength prior the match and the mean. And here I use standardized values with LO minus 1853 divided by 140. And let's see an example. The last edition, Russia against Saudi Arabia. Russia was the host, so the parameter for the number of goals of Russia will be nu plus an home advantage of host plus alpha delta Ri AB beta R bar AB. And for Saudi Arabia, you will have H as the away effect because he's playing away, and here the difference will be reversed, RBA, and the mean will be the same. And if, for instance, considering two what I call neutral matches between teams not facing the organizer, I will adjust nu. Instead, I drop the influence of the home effect. For forecast purposes, we'll add priors on the parameter derived as posterior from data of a learning sample. Is what I did usually in my predictions. And in that case, having the posterior distribution of a parameter, I can reconstruct the forecasting probability of elementary score lines for future matches. P future match in Ij equal U and V. Oh, sorry. And if you assume a Poisson distribution, you can take the mean of this posterior distribution according to this expression, the product of the two Poisson probability. And Y is ex-ante score lines data plus LO rating of future matching prior to these matches. Now, I tested several factors on the whole data set, stage, year, this home effect, the coefficient for the difference and the coefficient for the mean, and an interaction between the coefficient for the difference with the stage. So there is a slight effect of of group stage as compared to knockout, a little bit higher, but it's not significant. Here, it's varying, but not really very much. I put the first 86 and the last two, which is a reference here. Here for the venue, you see that there is, the host is a little bit higher, but not very much. Is in that case, the team playing against the host. But remember, this is in addition to the effect of the difference and mean in the Elo rating. So it's an additional effect with respect to this difference already taken into account. Now, this is the model for the regular time, and this is the model for the extra time. In terms of knockouts, intercept, I just kept the mean and the difference, and you see the parameters. So at the level of knockout is mainly the intercept and the difference between the Elo rating, which are the most important factor. At the extra time, we have a contribution of both, and especially a contribution of the mean with a negative coefficient. I have to make a correction to adjust the distribution of these two quantities from the ET sample to the RT sample, because I don't know in my prediction which teams are going to play the extra time. So I have to just base my evaluation on account of the teams playing the regular time period. So now the final model. So lambda, log of lambda for the regular time, for the extra time, and the ratio, the log of the ratio. So these are the coefficients for neutral matches and for all matches. And so you can apply it in a model if you want to compute these lambda values, just taking into account the mean and the difference between the Elo rating. And if you look overall, with here it's at the team level, but overall you get this value, and you come up with on the exponential scale of 0.3 lambda ET over lambda RT, or 0.29 with all matches. The formula at the team level is given here on the exponential scale. The lambda ET over the lambda RT, 0.455 exponential of these differences. So it's for the neutral matches, this value times the mean, and here for all matches is this value times the mean. Now a quick mention of the penalty shootouts. At start, I just want to take one half, and finally I see that people are trying to estimate the probability, so I made a little bit of, I know that has been studied a lot by Laszlo, by many people, and some of them have give talks in this seminar in S training. So it's a very simple study. If you assume YA, a binomial distribution, given the number of success of the team in any trials, penalty shoot trials, and the same for B, So you collect historical data and you report the number of success among the matches played with shootouts. And you can use, in that case, the Bradley theory, giving you the probability that A will win over B. It will be pi A over the sum pi A plus pi B. It's the Bradley theory model. I could have explained, but I cut this part because it would be too long. Now we can stop here and estimate pi A and pi B. The problem is usually we have very little information at this stage. So we have to make some prior assumption, and one of them could be a Bayesian approach with a prior distribution on this pi A and pi B. We can take a uniform prior distribution with here pi A over pi B, A plus pi B equal 1/2. So you take uniform beta distribution with A, B equal oh, I'm sorry, it's one, it's not 1/2 here. For uniform prior, the Laplace, it's 1. I put 1/2, it's 1, sorry. Now, we can derive the posterior, but we are not interested in that. We are interested in this ratio. It's a complicated expression, but it's easy calculated via MCMC, for instance, with the bugs software. So here I reported this expectation of a posterior distribution, and we're in rows, for instance, 8 putative teams playing the next World Cup: Ecuador, Netherlands, England. I put Iran and stop. I don't know who will be the second, maybe USA or Wales, and so forth, and France, Denmark. And here you see that, for instance, Argentina has a very good penalty shootout estimation with practically all teams. Same for Denmark. And sorry, James, but it seems that England has a problem with the penalty shootouts. At least it is reported in the literature. So what are the options we can use to meet our objectives? We can use overall estimated value for QKL based on the joint observed distribution. And just take the observed distribution, is this 3×3 table. You can take also the marginal distribution under independence, either a multinomial or a Poisson. And we saw that that worked not so badly. Or we can combine the two, and we will do that. Another option is to develop your own model for PKL in RT using a marginal Poisson log linear model that I'll show you, and take lambda ET equals 0.30 lambda RT. And it's not stupid because it's not too far from 1.1/3, which is expected from an homogeneous Poisson process. Remember, regular time is 90 minutes, extra time is 30 minutes. So if it's an homogeneous Poisson, that needs 1/3, and you see we found 0.30, so it seems that they are a bit tired, but not so much, and it's very close. You can develop a distinct model for each time phase, as we see before, and it's also a possibility. And so just to point out that the estimation how to combine A and B, we can use an empirical based estimation combining the frequency of the observed value and a prior value, and the prior is taken as V1 under independence, either multinomial or either Poisson, with two weights, and the weights is n, number of matches, divided by n plus k. K is a parameter derived from the prior distribution. So the smaller the k, the higher W, and the higher the contribution of the data. So if we do that, for instance, with the multinomial, this is the observed value for the classes in extra time. This is the value expected under independent multinomial, and this is the empirical base estimation, a kind of mean between the two, with the weight for the observed 1.4. And this is the same for the Poisson distribution. And you see we are not very far, a bit different, but not very far from the independent multinomial. The advantage of the Poisson is just have one parameter. Now the last option, and I won't miss it because it's the option used by most people now, is to run a simulation of a complete or partial stage of a competition. And it's a long way, but now with the power of computers, it's usually it's easily possible if you have enough time and enough memory. You run a complete simulation of all the process. For instance, if you know the teams entering the knockout, you can compute outcome probability of match according to win, draw, loss, or score lines in regular time. You sample at random the outcome of the match. If simulation gives a tie, then you simulate extra time models and sample an outcome. If the final outcome is again a tie, you simulate a penalty shootout of win, draw, loss, of win probability, make a draw according to the probability of winning, and you repeat that many times. Some people do it more than 100,000 times, and you compute the frequency of the draws, and you take that as the probability of response. This avoid probability adjustment formulae I give you, and this gives you exact selection of match undergoing ET. Now, quite a small discussion. Limitation of a procedure, small sample size is the problem, issue in going back too far in the past, relevance to borrow information for other competitions. Is it possible to borrow information? I'm not so sure of that. Is the problem of the knockout? Do we proceed with random draw at each step, and as in the, for instance, Champions League of the knockout, or do we proceed with pre-assigned allocation between groups, as in the World Cup and the Euro? That makes a big difference between the two kinds of tournaments. I use a very simple methodology. We can implement other effects and other covariates. We can implement other models with identified team effects. We can also use different approaches as random forest and machine learning. We have to test the forecasting performance of this option via probability scoring rules and their components using different models, statistical procedure, and compare with gold standards, for instance, the English bookmakers. There are other issues, and some of them, it seems to me, are important. How to assess the uncertainty in the forecast of outcomes. Probability of score lines or win-draw loss are themselves uncertain, and it's seen, for instance, if you use the Bayesian procedure, because you have a posterior distribution of probabilities. What about the value of forecast on the entire match outcomes prior to any match? You see, already on the internet, prediction of all the stage of the World Cup, including the winner. And I'm really doubtful about the value of such procedure. A list of reference, and not probably complete one, with some people of the S-training and of the roses. And also two quotations. Prediction is easy, predicting actuality is the hard bit, by David Spiegelhalter. And also some people think football is a matter of life and death. Assure it's more serious than that. Bin Shankly, a Scottish player, which was a famous manager of in the English Premier League. Acknowledgement for James, Christophe, and Andreas, for a colleague of myself, Sele, and a student. That's all.
Thank you very much, Jean-Louis. That was a fascinating
Maybe too
presentation.
long.
No, perfectly timed, perfectly timed. A fascinating presentation on something that a lot of us, as you point out, gloss over when we try and make predictions. We just have the final results, and those results could have been over 90 minutes or 120 minutes or 120 plus penalty shootout, all of which are have very uncertain outcomes. So thank you very much for that, and thank you also for reminding me that England are very bad at penalty shootouts as well. We've got time, plenty of time for questions and comments. So if anyone has questions and comments, please go ahead. Yeah, well, while people get their hands up, Jean-Louis, I'll ask you kind of the cheats question, I guess, is that if you're like me and you've just assumed that everything's normal, I've got my Poisson distribution to generate my goals for any game, be it group stage or knockout, did you do any kind of analysis to see what the difference might be in terms of the predictions?
I'm inclined maybe to stick with the first option. I think there are really two different options. The simplest one is just to take 1.3 the lambda parameter of the regular time, and it's the easy one. Is in fact what I did when I computed the probability for England versus Denmark. Even I take 1/3 because at that time I did not know it was 1.3. And I think I will more inclined to take the mean between the observed distribution in extra time and the mixture of this observed distribution, the one under the independence, using either the Poisson or the multinomial, what I call the empirical base. So in that case, I have a balance between what has been really observed and what we can expect under a model which makes sense, and independence with multinomial and Poisson. And in that case also I may take into account some relationship given by the observed data between the two number of goals.
Thank you. So we can still cheat a little bit then.
But anyway, I think the key question maybe is, do we have to proceed with the simulation of all the process, or do we have to recourse, I think, the old-fashioned way with models? Maybe it's more the question of in the light of data analysis, people are more inclined to simulate everything and not rely so much on model distribution. To that extent, I'm a bit old-fashioned statistician and testing hypotheses. And so it's, I think, one main question. Although if you simulate, at some point, you need models too.
Absolutely.
No.
So, would you say it's? I mean, I guess it's possible in principle to work out all the probabilities of each country winning the World Cup, but that must be a fearsomely complicated calculation, Jean-Louis. Okay, well, I'll open the floor for questions. Roger, go ahead. You might still be on mute, Roger. Can't hear you.
I beg your pardon. Can you hear me now?
Yep, got you.
Yeah. Yes, the two lessons I take as a betting man rather than an economist from that is that if the score is level at 90 minutes, I should bet on it finishing as a draw after extra time. I've got a 60% chance, and I've also got about a 60% chance that no further goals will be scored. So that's useful information. A comment I would make about the bookmaking industry is, why are they so insistent on taking bets of the score at 90 minutes rather than the result?
My observation was that over the last editions, there had been quite more goals scored at the end. At the end of the regular time and even in the stoppage time, as compared to the oldest editions. And one possible explanation I had for that is, first, the coaches are too much confident. They are not as in other sports, for instance, in basketball, managing their team very well for the end of matches. Another reason, they had changed the way the goalkeeper is playing. Now he has to play with the foot, with his feet, as compared to before with the hands. And if you remember past matches, there were a lot of passes to the goalkeeper at the end of the match. And that way, a way to preserve the score, as compared to now, they are obliged to go forward or to let the goal play with his feet. And it's not always a good solution. Maybe I tried to look, I think there is a study to make to this goal really at the end of the period, and especially the regular time and the stoppage time. It's very, you see in many instances now, there is even the level, the score, even they can win in 1 or 2 minutes now.
Yeah, I think
so.
so.
That makes the issue really difficult to predict, you know.
Yeah, absolutely. You may not have caught, there was a game in England's third division the weekend before last, which at 90 minutes was 2 each. This is a game between Charlton Athletic and Ipswich Town. And there was 6 minutes of added time put on. And at the end of added time, the score was 4. So there was 4 goals in 6 minutes of added injury time. So that definitely, there's more minutes of injury time, it seems, and there certainly seems to be lots of action. Roger, I don't know if you wanted to respond to any of Jean-Louis' responses to your questions.
No, no, thanks. The only other point I'd make, I noted Jean-Louis' references to the 19th century at the start of his presentation. Just as a matter of interest, I'd like to let you know about something called the Beaumont Rules from the 19th century, which was that the first goal in any match only counts as half. That got away from all the need for extra time and penalty. Not all the need, because it was goalless, you still needed a way of dealing with it. But I thought that was a fascinating idea, and I'd quite like to see it experimented with now.
I did not know that. But it's not very well known, no.
No, not so well known. Thanks, Roger. Thanks, Jean-Louis. Matteo has his hand up with a question.
Good evening.
Yeah.
I don't understand why you use the Elo rating for short tournament like World Cup or Euros, because I think that in this tournament is very important how the team arrived to the tournament. So the form in the last maybe 5 or 10 matches. So maybe with the Elo that compute all the last year, if I remember well, of matches, maybe you have you don't have a precise result. For example, I mean, in at the moment, Italy is third for the Elo rating, but we know that if Italy faces any of the big team, is more likely to not win the match. So I don't know. Maybe you can use a short Elo for the last 5-10 matches for compute goals for short tournament.
So what is your suggestion in that case?
I don't know. Maybe remodel the Elo system just for the moment of form of the team. Because I think that like I say before, the Elo compute all the year of matches, so maybe it's a good model for a long tournament like a championship. If there is a Elo for club team, maybe is good for compute all the goals from the Premier League, maybe. But for short tournament, I think it's very important the form of the team.
The Elo rates I use here are the Elo updated after each match. So even it's not the same Elo for a team during all the competition. It has been updated after each match. So for instance, when we look at Brazil against Germany, if Germany beats Brazil with a very large score, after the match, the Elo rating is updated in favor of Germany. And so I think the Elo, despite it looks very simple, I think it's a very good criteria to update information about the potential value of a team. And I was surprised, but I got easily all these Elo ratings from the site on the results of this World Cup, Euro, and so forth tournaments. So maybe what we can do is the problem of the learning sample. You can incorporate results outside the competition, or just in the Elo rating, they incorporate, for instance, in that case, results between matches played by the nations in different instances. And in some extent, they incorporate, they borrow information from other competitions. But for instance, in my case, the analysis was carried out only with its 9 editions plus the Elo ratings. So it's a mixture of pure competition and extra World Cup information. So I don't know how people build their learning sample. No, it's, I think, a key issue, probably as important as the statistical procedure itself. No, the learning sample.
Okay, thanks.
No,
No.
because we can also take all the process before entering the final tournament. No, all the qualification before. No.
Yes. No, my suggestion is just maybe consider just the last matches and not all the last year.
But the Elo rating I used was this Elo updated at each match.
No, yeah, I understand.
Yeah. So you mean maybe you can compute the Elo rating and the variation between the last two Elo ratings, no? If it's going up or is it going down, no? Something like that,
maybe.
no?
Yes.
The derivatives of the Elo function.
Yeah, I guess the suggestion is something like that. I guess if you took it from the eloratings.net website, I don't know, they may already incorporate some kind of weighted adjustment for more recent matches.
Mm-hmm.
I know that England has dropped quite significantly in their ratings. England's now 14th. 1 year change of -7, which reflects the fact they've been doing very badly over the last year. So it could be that they weight more recent games, but I mean, by the formula by itself, of course, means that all games, including the recent ones, were counted in the formula.
We may tempted to put many covariates and at the end be obliged to drop a lot of them. So it's the problem with some procedure now. They started with a lot and they perform a kind of lasso, things like that, and they drop at the end maybe 60% or 70% of the initial covariates. So
yeah, absolutely. Thank you, Matteo. Any more questions and comments or any follow-ups that you may have, Matteo, as well? Stefan.
Hi, Jean-Louis.
Yes.
Very, very interesting and very informative. So it really relates a little bit to the last question, which is sort of to say, well, I mean, there are sources of information that you're clearly not using.
Yeah.
So why, in some philosophical sense, so what's the objective here? Why, we could add extra sources of information which would presumably improve the forecast. So what's the rationale for not doing that? Or is it just to say that this framework gives us this answer? Is it like a horse race where we're just looking at competing methods? Or how do you think of this in terms of essentially what is the best approach to thinking about forecasting events like this?
It's a tough question. As I said, at some point, even in my career, I was inclined to put a lot of the information and make the selection at the end on account of contrasting observation and predictions or of expected value. And so a blind approach, whatsoever the causal inference could be. And now I'm more inclined to use a very small number of covariates using informative covariates, as for instance the Elo. And I put in the reference a couple of articles, and especially the last one in Statistical Science, indicating the value of this criterion, the Elo. if you are now in the vein of a causal inference, you will be a part to some extent of machine learning, because in that case you will try to imagine what makes the difference on the field, really on the field, and you will be inclined to use maybe information on the players, on the interaction between players, something I think is lacking in the models I'm using here, no? Maybe to be able to have a covariance indicating the ability of a group to perform on the field, no, depending on the individual players and their interactions, no.
Yeah, I mean, well, so if I wanted a causal explanation, I don't
Yeah.
think this is the way I'd be going at all,
Oh.
right? So I mean, I think that, so you know, in that sense, but I think this is what you're engaged in is a forecasting exercise, right? So you're not really interested in why this is true. You're just saying this.
Yes,
And
exactly.
you're saying ELO is a great statistic, which it is. I mean, ELO is a great statistic, but there clearly is more information out there as well. I mean, there's that clearly. We can't think that. I mean, partly because this is the performance of the players, and the players perform in fora other than the national team. So
Yeah.
to take it, so to think that the result of a team, of a national team consisting of players who played lots of other games, I mean, clearly the current form of the players matters. I mean, I can't think you're going to deny that. So that surely, if I wanted to say what's the best forecast, this is unlikely to be the best forecast because that information is just not included, which is clearly relevant. Or would you say that, or would you disagree with that? Would you say no, this is still going to be the best forecast, even ignoring the form of the players in their league games?
You make a study on that using, I think, the value, I would say the dollar value of the players, no? And it gave a very good forecast, no?
Yeah.
I remember one of your presentation.
Right.
No?
Yeah, that's true. But I had a specific purpose in that, which is to think about whether, I mean, my purpose in doing that is simply to explore how reliable the market is in predicting. So that's my reason for doing it. It's not because I'm interested in making good forecasts. I'm not really. So that's what I'm coming back to, is what's your purpose in this, and you know why. Given your purpose, what's the reason to exclude information?
No, if you have the view of the betting market, you are inclined to predict well the unpredictable. I mean, the surprise, because he's in that kind of match that the return are the highest. No, there is this unbelievable situation that the most difficult match to predict as the most profitable, no, in the betting market, and it's completely contradictory. You could have a good performance on the scoring and a probability score and earn no money at all, even lose money, no, because you are predicting very well easy matches, no, to predict, no. So I think we need a goal, no, and this was not really transparent in my talk, no, the goal.
Right.
What to predict for? So it's your question, if I understand.
That's it. That's my question. What's the answer?
So in that case, maybe I have not to drop the 19 match, no, the extreme match I put aside, at least to test the assumption. But it's amazing that you have about one at each edition, no, in the final, and you know, the odds for these matches are extreme. And now also the betting market is oriented very much to very elementary results, no? no more win, draw, loss, or even a score line. So it's really a challenge. I don't know exactly how they could put odds on this very specific event in the match.
Well, you can put odds on anything, right? Oh.
So we need, in each case, forecasting, we need a goal, and I forget that. Not only a good probability score, no?
Well, yeah. Are you going to bet based on your model? That's the other question. That's another way to put it.
No, the last question I have is, what is the value to predict all the process right now? I put a reference, and there are, and I noticed, for instance, that 538 is quite more conscious now than it was before. I did not see any prediction of the whole process now. I just have a look before, and it seems to me that there are more cautions than before, but other sides give all the process, all the qualification. Even they say the final would be Brazil against, I don't know, Germany or France. Or I think this kind of forecast, I think, is rarely helpful, no?
In what sense?
In that sense that it's often wrong, no?
Well, so one thing is, using your model, how often would your model have predicted past World Cups accurately?
I think I can do it, but I don't feel comfortable to do that. Really, I don't feel comfortable, because there are, at some point, if you have probability very close, if you have a kind of uniform distribution of the different possibilities, just a matter of chance, no?
Well, yes, but you were just casting aspersions about other people's forecasts. So, if you're going to say that other people produce bad forecasts, and you're not prepared to stand by any forecast of your own, right? I mean, that's a little bit unfair, I think, isn't it? I mean, I'd like to see your forecast compared to 538, for example, see how you do, or James's or other people's. I mean, these are horse races we want to see the answer to, right?
I have a question in my discussion, how to report about the uncertainty of the results. Nobody reports that. And it seems to me that it would be very useful to report some criterion about the uncertainty of the predictions, some interval, forecast of intervals, something like that. Because, for instance, if you are doing Bayesian statistics, you are faced always with this problem. You end up, for instance, with probability of win, draw, loss, but each of them, there is a distribution, a joint distribution of these three possibilities for the probability themselves. So even if you imagine doing a simulation, you have to make a double draw in the distribution of this probability, and making a draw of the probability, draw now a 0, 1 with that probability of Bernoulli. So you have to make a double sampling if you are doing Bayesian, and so you will add uncertainty in your result naturally. Here I was at some point classical. I take the expectation of the posterior distribution, so I take the mean of all this possibility. And so I'm concentrating on the mean tendency, but I think we have to work on the uncertainty of these predictions. No?
Yeah, no, I think that's a great point. Actually, no, you're right. Absolutely, I think that's really interesting.
Okay, we have hit exactly 4 p.m. So we have hit our time limit. So thank you very much,
Stefan.
Thank you, Stefan.
Questions.
Thank you, everyone else, for your inputs. It has been another fantastic and very informative, very interesting session. So thank you, everyone. By the time we meet, actually, no, next week we'll still be able to meet one more time before the FIFA World Cup starts, when we can start to see just how good everyone's forecasts are. We'll meet this time next week when Pete Brutus, a regular member here for the Roses Talks from the Appalachian State University, will present positional segregation and career length in Major League Baseball in the 1990s. So just in time for the Football World Cup, we'll switch to baseball. But I look forward to seeing you all next week. If you're an S Training member, thank you for being with us. And if you want to join us again, get in touch. I can add you to the list. But after all that, thank you, everyone, and see you all again soon.
Thanks very much.